Modern machine translation systems are governed by a strict dependency. They require massive, supervised bilingual corpora to function. Sequence-to-sequence architectures rely on these explicitly paired vectors. The network needs an exact target output to compute its loss function and update its internal weights. This creates a hard limit on global scalability. For language pairs like English-Urdu or English-Romanian, datasets of that size simply do not exist. Global translation scaling currently stops where structurally aligned human data runs out. Researchers at Facebook AI approached this limit by asking if state-of-the-art translation could be achieved using entirely independent, disjointed monolingual corpora. This scatterplot represents an unaligned monolingual dataset. Trying to map this to another distinct languages dataset without a dictionary or parallel texts is mathematically an ill-posed task. To force a solution, the research team engineered a specific three-step algorithmic process to extract structure from noise. The implementation of this process yields a surprising result. In zero-shot environments, legacy statistical models can rival or even surpass modern neural transformers. This suggests that the core of the translation task might be found within the independent internal characteristics of each language. Without parallel data to guide gradient descent, the model starts completely blind. It requires an injected prior to jumpstart the learning process. By analyzing massive amounts of unaligned text, the system generates cross-lingual embeddings. It maps sub-word units across the two languages, based entirely on how frequently and in what contexts they appear. Looking at this clustered scatterplot, we see the result: a rough word-by-word mapping between the two isolated datasets. This initialization produces ungrammatical, near-incomprehensible sentences, but it successfully locks the underlying semantic topology between the two languages into place. The second principle corrects that grammatical chaos by training robust language models exclusively on the separate monolingual datasets. This continuous wave pattern illustrates the data-driven prior. It dictates the mathematical probability of how sentences structure themselves in a given language. The model operates as a denoising autoencoder manifold. If a translated sentence lands outside the parameters of proper syntax, it registers as noise. The model exerts an algorithmic gravitational pull, forcing the disconnected, roughly translated words from the first step to conform to the syntactical reality of the target language. The final mechanism is iterative back translation. This engine converts the unsupervised void into a supervised learning task. This dark red scatterplot tracks the operational loop. A forward model translates an observed, verified source sentence into a noisy, theoretical target point. A backward model then takes that noisy target and reconstructs the original source sentence. The original source sentence acts as the absolute ground truth. The spatial discrepancy between the initial input and the final reconstruction generates the precise error signal needed for backpropagation. By iteratively generating these synthetic pairs, evaluating the reconstruction, and adjusting weights, the network becomes its own teacher, bootstrapping its way toward fluency. The research team implemented these three principles across two distinct architectures, starting with a standard neural machine translation sequence-to-sequence model. They apply byte pair encoding across both monolingual corpora simultaneously. This joint tokenization drastically reduces the total vocabulary size and eliminates the problem of unknown words in the final output. During training, the network minimizes the autoencoder loss function. It intentionally drops and swaps words within a single language, forcing the system to learn how to reconstruct the proper sequence. The critical architectural constraint lies here. The parameters of the encoder must be strictly shared across both languages. By utilizing identical lookup tables and weights, the network is forced to project both languages into a single language-agnostic latent space, a mathematical interlingua. Because the internal representation is shared, the structural denoising behaviors the model learns on monolingua text effectively generalize to the cross-lingual translation task. The researchers also applied these identical principles to a legacy architecture, phrase-based statistical machine translation. Statistical models operate entirely differently from neural networks. Instead of fitting hundreds of millions of continuous parameters, they rely on rigid phrase counting and conditional probabilities. To initialize the system, the model extracts the most frequent phrases, aligning them using a rotational mapping known as a Muse matrix. This populates a complete phrase table, establishing a baseline vocabulary map without any human parallel alignment. The system then runs its iterative back translation loop, utilizing smoothed n-gram language models to aggressively correct and filter the noisy synthetic data it generates. In a zero-resource environment, this statistical rigidity is an advantage. Neural networks are highly prone to overfitting when trained on noisy, unaligned data, but the phrase-based model simply counts occurrences, filtering out the errors through sheer probability mass. Tested on the standard WMT 2014 English-French dataset, the unsupervised phrase-based model scored 28.1 blue points. It achieved this without referencing a single parallel sentence. That score represents an 11-point leap over the previous state-of-the-art for unsupervised translation. This line chart plots the blue score of the unsupervised systems against traditional supervised models trained on varying amounts of human data. The unsupervised statistical model manages to completely catch up to a supervised neural network trained on 100,000 aligned sentences. The absolute peak configuration combines the two architectures. The team achieved their highest performance metrics by using the cleaner synthetic data generated by the statistical model to fine-tune the neural network. The system does have limits. Ablation testing proves that running more iterations of back translation eventually plateaus. It cannot compensate for a weak initial embedding alignment or poorly trained language models. The reliance on massive parallel corpora is now a conditional requirement rather than a fixed necessity. Today, machine translation can now be executed using nothing but the internal structural data of the languages themselves.